So, Igor, please go ahead. The floor is yours.
Thank you, Edmund. Let me know if you can hear me clearly, and yeah, interrupt me if there are any questions, if something is unclear.
We can hear you.
Okay, great. So my name is Igor. I'm technical consulting engineer supporting Intel compilers. I've been doing it since 2008 at Intel, and I'm proud that today we are bringing to a market the compiler which is called Data Parallel C++, and that's why today we are going to talk in a bit more details about programming with a SQL, how to use the Data Parallel C++ compiler to compile the SQL code, and focus will be definitely not on all in-depth concepts of SQL itself, but more on details of implementation from our side. So what you can control at runtime, how does it work? I try to combine quite useful links all together on these slides, so that once you start and you need more details, you always can go ahead and follow these links for more in-depth information. So we will start about basic concepts of what is DPC++ and SQL, then talk about Intel compilers, our packaging, what do we ship, and where can you find DPC++ compilers. And then quite promptly, we should switch to SQL basics, talk about what are buffers, so memory model concepts, execution memory, execution model, and so on. So we'll talk about all these details. And I divided it into two parts, but actually it makes more sense to consider this presentation as continuous one. But I want to stop at some point and show you a few examples from our Intel Dev Cloud. Klaus Dieter was talking about a bit earlier, because there are some interesting getting starting exercises which you can even follow yourself. And then we will talk in more details about implementation details of how a compilation and execution of applications happens and so on. So I think it's not a secret that heterogeneous programming is de facto a standard nowadays in existing HPC and non-HPC domains, right? So the ability to offload some calculations to accelerator are quite important. And the thing is that all existing methodologies or programming models had some kind of disadvantages. Quite often they are limiting you to use one vendor only, right? Locking you to one vendor, like what's happening with CUDA and NVIDIA. From the other side, there were some models like OpenCL, right, which potentially allow you to program for different vendors and different accelerators. But the problem for these models is quite non-competitive performance in many cases. And that's why Intel decided to bring this new industry initiative, called it One API, right? And DPC++ is in the heart, in the middle of this initiative, right? So what is DPC++ and what is SQL? SQL is a standard which is driven by Kronos Group and which has been available for developers for a while. However, this standard historically was based on OpenCL. So even in the standard itself, it was a statement that it is an abstraction over OpenCL layer. When Intel was involved in the evolution of this standard, it was identified that having only one backend, only one technology on the lower level as OpenCL is definitely a limitation. So that's why in the latest standards of SQL, this limitation is relaxed, and now actually SQL can be considered as a C++ implementation, right, which is pure C++, so it doesn't have any new keywords or something which violates C++ standards. So it is abstraction based on C++, which allows you via templated classes and objects to perform calculations on accelerators. These accelerators can be different. And since it's abstraction, on the lower level, there should be some kind of lower level API. So historically, it was OpenCL, and nowadays it can be any backend actually. So there is no limitation by standard itself what can be used under the hood. Again, since Intel started this initiative, many changes were introduced in the SQL, which were brought by Intel and by community. I will show you how the ecosystem looks like, but the development is happening in a very intensive way. Many new features were introduced in the latest standard SQL 20, which is now a standard all vendors are trying to be compatible with and conformant with, and Intel is doing the same. Note that existing SQL, latest SQL standard is available by using this link. And nowadays, the implementation of our compiler, so since I talked a bit about what is SQL, right? Then the obvious question, what is DPC++? We recommend to think about DPC++ as an implementation of a SQL. So it is a compiler which is expected to be 100% conformant with a SQL standard. But on top of that, if we identify some gaps and we want these gaps finally to be implemented in the SQL standard, we are implementing additional extensions, community extensions on top of the Chronos SQL. It doesn't mean that we are not following SQL standard. We just want to make it better, and that's why it's like an iterative loop. So we are introducing community extensions, and we are trying to push these extensions back to the next standards and so on. So it is an iterative process with a Chronos group and SQL standard committee. For a full list of community extensions, you can take a look on this link. We nowadays have a long list of additional improvements which are available. And note, by the way, that the majority of these improvements we initially introduced, they were ported and accepted by the SQL 2020 standard and even improved there. The reasonable question is, how many features of existing SQL 2020 standards are already supported by DPC++? We are improving it significantly from one version to the other, so it's really a good practice to take a look to this link and check which features are expected to work nowadays. We are on our way to have a full support for SQL 2020, but we are not there yet. That's why existing state of a DPC++ compiler is that it actually support a mix of previous SQL standard, current SQL standard, and some language extensions. And all this is covered in this table, and it's showing, okay, this is what we do support nowadays, which is we keep supporting from all the standard, but going to deprecate, which is also important for those of you who are aware about SQL and already using some features. Note that SQL, we are on the process of migration from one SQL standard support to the other. We are deprecating and removing some of the older features which are replaced by new features in SQL 2020. And that's why we are listing version by version what is exactly supported in which compiler package. Any question here? Okay. Again, I said that almost on each slide, I will have some quite useful links. So here I'm going to talk about more way how we implementing DPC++ compiler, right? So the development is happening open source. So we have our GitHub project for Intel LLVM compiler. It's not actually only for DPC++ compiler. We actually have different compiler technologies available. So we do have our classic compiler based on IL0 technology, and now we also introduced new compilers which are based on LLVM technology. So DPC++ is a compiler based on LLVM, as well as our regular C++ compiler. That's why even the package called like this, right? So again, because we don't consider DPC++ or CASTIEL as a new language. It is a basic C++ 17 code. Under the hood, we also need to have a runtime, right? And for runtime, we also open sourcing the project. And so what is quite useful is that even for debugging purposes, you can always get all the sources of a compiler and runtimes and graphic compiler as well, and understand what's happening under the hood, which is really great and which was not happening in the past for Intel compilers. The only note I need to mention is that we also ship our compiler in the form of binaries, right, with our toolkits. So this compiler may have some differences with what we are open sourcing. And it doesn't mean that it's better or it's worse. I mean, it has some closed source optimizations, which we are not open sourcing. That's true. So from that point of view, for host side of your code, it may give you better performance. I mean, the compiler which we are providing as binaries in our toolkits. However, on the GitHub, you can get the latest features, right? So all the latest features goes directly to a GitHub project, and that's why there is always a gap in the time, like the new features are already here, but an Intel compiler shipped with a toolkit, you may see these features 2-3 months later. So there are pros and cons what to do and what to use. The other advantage of an open source project is that everyone can contribute, right? And that's how the NVIDIA GPU support was introduced in the GitHub project, as well as AMD GPU support. So actually, in the open source project, you're getting the support not for Intel CPUs, GPUs, and FPGAs, but also for NVIDIA GPUs and AMD GPUs. I think one bit correction to my statements that an open source project, we don't ship FPGA support as far as I remember, but maybe I'm wrong. So again, nowadays SQL standard allow you to create this abstraction over any backend technology. So the concept of backends was introduced. So think about backends as low-level API, which is finally implementing what you're trying to do. And historically, OpenCL was there, and it is still there. But Intel also bringing own low-level API called Level 0 and opening the specification so that any vendor can go ahead and implement this low-level API. The CUDA backend is also there, and as I said, recently it was AMD backend called ROCm edit to open source project. For samples and SQL standard conformance tests, you can find these two links, which are quite useful. So if you want to see how all the concepts we will talk about today may be used, right, from all angles, from different ways of usage, then please follow these links and take a look on the tests. This is a very good way of learning what you can do and what you can't. A few words about SQL ecosystem. As you can see, it's growing, and there are more and more vendors supporting different implementations. So you can see that DPC++ here, as I said, supporting all Intel hardware plus NVIDIA and AMD GPUs. But our vendors allow you to target even more different hardware vendors. And you can see that CodePlay has some support for ARM, IMG Power, and so on. This actually giving you almost unlimited um, options, right? And writing your code following the SQL standard may allow you to finally run on so many and diverse set of accelerators and hosts, and this is really great. And the task for all these vendors, and I would say that major vendors here are TPC++, Compute CPP, and HipSQL, as well as TriSQL. But I think that these are first three implementations which are the most known and in use, right? And there are many research papers and very nice investigation and cases of usage and comparing the performance versus vendors and so on. As I said, one of the important goals for Intel is not just bring a new programming model which allow you to target all the devices, but also one of the goal is about the performance of this diverse set of devices. So we are paying the attention to this. We are already have quite good results on different vendors, and today I will talk a bit about this. If you want to take a look on how does SQL work on NVIDIA hardware, I also collected for you some links on the webinars which were delivered by CodePlay, since CodePlay launched the support already more than a year ago. And the implementation, I would say, is mature enough and delivering quite good performance on A100 and our GPU cards. So please take a look on these links for more details. I don't want to deep dive, so all what I'm going to talk about today on the high level, the basic concepts of SQL, they should work on any hardware, and that's the idea. So a few words about packaging of the compilers. I want to give you a few basic insights on the compiler architecture, right? That actually in any modern compiler there is usually a compiler driver, which is a command which you use to run the compilation process, right? And this tool may do a lot. So for example, it's not only doing compilation, right, but it's also doing linking. And the linker historically is always a different tool, which Intel, for example, never shipped with a package. So that's why we always need to have some kind of GNU linker or Microsoft linker on Windows to finally produce some binaries. So, and that's the task of a compiler driver, is to correctly parse all the options you are passing to the compiler, all the paths to the libraries, and to include headers and orchestrate the whole compilation process. So it may consist of many different stages actually. And that's why we do have a different compiler drivers. So we have one driver for C codes and the other for C++ codes, right? And once the source code and all these options are passed to a real compiler binary, then it usually consists of three parts. It's front end, middle end, and the back end, right? And middle end is usually here. I a bit oversimplify this picture, but the idea is that the real code generation, right, the translation happening later and not on the moment of the invocation of your compiler driver. So that's what I wanted to highlight, because nowadays we have a diverse set of different compiler drivers, and you shouldn't be confused by that. So, and on this slide, I'm showing this diversification. So nowadays, as I told earlier, we have the compilers based on our proprietary IL0 technology. And if we go back to this slide, this means that we were generating our own IR, IL0 IR. We had proprietary optimizer and code generator. And nowadays we are reusing some parts here from LLVM. I would say majority of code is coming from an open source CLang project. But on top of that, we are also enhancing optimizer and code generation from our side. So that's why you can see that nowadays we have L0 classic compilers and LLVM compiler, and we are in the process of migration from our classic compilers to LLVM based, which means that at what moment we will move to the legacy mode and stop supporting these compilers. So that's why it is it's a good guide and recommendation from our side to start porting your applications. And finally, this will allow you not only to, if you're using ICC, for example, or Intel Fortran compiler, not only to keep using it to target CPUs only, right? But if you migrate to a new LLVM compiler, you can easily introduce offloading to GPUs as well in your code, because it will be much easier to do than with classic compiler. So the main difference is the target devices which are supported. Of course, consider these compilers as quite different compilers, since the optimizations and code generation are different. Actually, all these compilers keep supporting OpenMP threading and vectorization support, but OpenMP offloading is only supported in LLVM-based compiler too. So that's why any kind of acceleration on our devices than CPU may be used with LLVM compilers only. Good news is that all compilers we are shipping are cross compatible, so that it means that you actually can keep compiling some models with ICC and others with ICX. But again, my recommendation would be to try to switch with all project to ICX and fine-tune the performance and so on. A few words about the versioning, since you will probably try it soon on the dev cloud or on your own machine, is that for our classic compilers, we keep counting versioning in 2021 branch. So the latest version of Intel compiler ICC or iFort is 2021.5. However, the compilers based on LLVM are versioned as 2022.0. So we, note this difference, it shouldn't confuse you. And note also that there is a naming of one API package itself and the name and the versioning of a compiler. So the existing version of one API, the latest one, is called 2021.1, right? And the compiler version, which is in line there, is 2022.0. And there is actually a minor version which also introduced some updates we introduced there. One important link on this slide is this one. So as you can imagine, we are talking, when talking about DPC++, we're talking about heterogeneous programming, right? And the installation may be a bit more tricky than the usual installation of a compiler for CPUs only. Because here, for example, if you talk about GPUs, right, you also need to have GPU drivers installed. You also need to add the user to some groups to allow the executions, like renderer group, for example, or video group in the past, video group, so that the user is allowed to calculate something on GPU, right? And you need to care about some additional stuff like hand check, because if the workload is relatively large and it's calculating on GPU, there is a protection which is on by default usually, right? Which will check for you if workload running too long, and it will stop the execution. So all this is carefully explained in our installation guide. Here I provided a link to on Linux, but it's easy to find it on for our OS, for Windows too. So pay attention to these details, because usually if you are going to install it on your machine, you need to carefully follow all the instructions. And note that you need to install one API package and also the drivers itself, which is quite important, and it's a separate step. As I told, the OpenMP is also supported by all the Intel compilers, but offloading with OpenMP is supporting with only these drivers, which belongs to LVM-based compilers. Still same way to enable it, the QOpenMP option like in the past, or with a let's say more C-lang syntax with -f option. But pay attention that now we ship with our compilers two implementation of OpenMP runtime. One is from Intel, FI OpenMP, and the other which coming from C-lang, and it can be linked and used with -f OpenMP. This is, by the way, quite useful hint for issues troubleshooting. If you observing some problems with OpenMP, then switching to open source may give you at least some understanding what's happening and isolate the problem to OpenMP runtime if you're switching between two different implementations. Or the problem may be in both, which is a rare case, but it still may happen, right? So maybe something is wrong with your code itself. And to enable offloading, you need to specify the additional option. And I'm not going into more details. Here is the link with some basics of how you can use OpenMP offload features. But tomorrow we will have a nice talk delivered by my colleague Alina, and she will be talking about OpenMP offloading in Fortran. And I think this is a spoiler from my side for tomorrow talk. So now let's switch to basics of a SQL. What is the main idea and how it looks like? I will show you a very simple application, but it's quite nice to show the basics of a concept and the concepts. In principle, the way how a SQL application work is that it now consists. It's a single source application, which means one source contains both host code and device code, right? And obviously that the host code will be executing on the host with the host memory, right? And the device code, there is a special mechanism how SQL allow you to execute the device code. So there is a special object which is called command queue, and you create the command groups, different command groups, and submit these groups to the queue. So there may be many command groups submitted to one queue or to multiple queue. So all this is possible. And this command queue is finally you link to the device. So by creating the queue, you are picking up some device. It's not necessarily should be GPU, right? But you need to think about it that this accelerator, and in many cases is GPU, right? It will have its own memory hierarchy. That's why there may be a requirement to control the memory management, right, between host and device. So in the simple way, you need to copy it back and forth, right, all the time. But with unified shared memory, or with shared memory between host and device, there are other options how to do it. But usually, in any case, the memory copy will happen from host and device. So it's quite high level picture. And now let's take a look on very simple SQL application code. So I will highlight for you a few markers in the code which help you to identify the host code and the device code. So usually you need to pay attention to the queue object creation, and this queue object is coming from the SQL namespace. This is a marker because once you're doing queue submit, as we talked earlier, we are submitting the common group to this queue. And inside this code, there is also usually parallel for invocation. And this is a marker where actually the device code is started. So this last argument we are passing to parallel for is actually a kernel. It's a lambda function, but it's defining a kernel. So a kernel is a basic terminology term in GPU programming, and it reflects this code which we are going to execute on the device, which will follow SPMD programming model. So it will be duplicated many times depending on the number of threads, or in SQL terminology, work items. We will talk about it. So this code may run thousands of times, right, on different execution units. And we need to care and provide the index, right, the different data to these execution units. But in principle, what I want to highlight here is the majority of the code is a host code, the major part, right? And the only part which is a code which is going to be executed on the device, a kernel code, is here. So take a look to the QSubmit operation and then to parallel for invocation. These are the markers for you. Yeah, feel free to ask any questions. Also, quite important for SQL programming is the understanding of the scopes, right? Because in different scopes, you can use different features of a C++ and different objects and classes. So obviously in application scope, you are free to use whatever you want since it's a usual host code. But in SQL, there is also a common group scope definition, which goes after the QSubmit operation and before parallel for invocation. So this part is called common group scope. And quite often you need here to define these accessors like done here. We will talk about it later. But there is also device scope. So all what you use here, right? And there are special mechanisms how you can use the data inside the device scope, or which features are allowed to be used in the device scope. So we are talking about SQL. It is a single source concept, right? Which means device code is in line to your one file code, right? But the thing is that for device code, you cannot use all C++ 17 features which you can use outside of the device scope. So, for example, like exceptions cannot be used here, or dynamic polymorphism is not allowed here. So virtual functions and all that stuff are still not supported well, while templates are quite okay to use inside. So static polymorphism can be used as well. By standard, there is a list of limitations, but obviously it's coming from the specifics of a device itself, right? So there are some limitations to think about. So finally, depending on what you declare in the different scopes, right, there may be different ways of usage these objects and different goals you may following. So now let's talk with quite basic concepts, and the memory model is quite important. So there are three different ways how you can work with memory in the SQL. Again, it's not about your host code. In your host code, you can do whatever you want. It's more about the bridge between your host code and device code, because the data is one of the fundamental basics, right? So the main idea of acceleration is that you have some data, right, allocated on the host, or even you don't have it, but you need to calculate something and you need to bring this data back from GPU. So it doesn't matter, is it coming originally from host to device when you calculate something and mapping it back, or it's just you creating this data from the device side and then you're copying it back, but definitely you're doing it back to some pre-allocated data on the host. And there are three major concepts. Actually, there are two major concepts because these two are quite similar. So buffers is an abstract view of a memory. So it's some kind of a wrapper you are using, which help you to make it possible to access your data inside the device code and to copy the data, right? To transfer the data all the time from the host to device when it is necessary. And the images, it's a similar concept. It's just a matter of what type of data you can use inside and what type of additional functionality you want to apply to this data. So it just has a more um, APIs to do image processing specific operations. So images are actually a subset of a buffer. So these are the corner cases of a buffers, but the concept is exactly the same. And the alternative concept is to use unified shared memory, right? So, which is a pointer-based approach. So it's not an abstract view of a memory, but you allocate directly the memory from a host side on the device side, or you're using shared allocations, and you're working more in the, low-level controlling manner with the memory. And this is quite similar to what is happening in CUDA, for example. So while buffers were derived from the OpenCL concept, unified shared memory is more or less the model coming from regular C++ or CUDA. So now let's talk about buffers in more details, right? So imagine you in your code, right, in your host code, you have some data. It can be plain array, it can be vector or floats, whatever you want, right? Um, so again, in these standard containers, you don't have any way to make it possible to move this data to device and back, right? So that's why we need to create a class called buffer, and you need to encapsulate your data into these additional containers, right? So that's why we're creating the buffers here. And we are using the host vectors or pointers, whatever you want. And this buffer encapsulates the data, and it allows you to control the memory management and to control the memory copy operation back and forth from device to the host. The important thing is that once you created the buffer, by standard, you are not allowed to change or modify this initial data, right? So adding something to a vector A after you creating the buffer is an undefined behavior until the buffer is destructed. Any question on the bridge? I hear someone is not muted, so I would appreciate if you can go on mute. Yeah, thanks. So, okay, this is, I think, clear, right? The next step is, as I told earlier, and it may be a really first step, is that we need somehow to link with the device, right? To create this bridge between our host code and the device and select some device, because SQL doesn't limit you to use only one vendor and one device. So you can have multiple vendors and multiple devices in your code. And that's the why the Q class were introduced. Note that all these classes are templated classes in most cases, like buffers. The Q is not a templated class, I believe. So the queue will submit the common groups and actually help you to execute some kernels on the device you pick up. There is a special mechanism how you can control the device selection, and I will talk on the next slides, but it depends. So you can control it at runtime, you can control it at compile time by modifying the constructor, right? But here we are creating the queue with a default constructor, and that's why we will pick up some default device. I will talk about what kind of device will be used in that case. So there is a special logic on the devices which can be used. So by default, the runtime will detect all the devices available in your system, and devices may be very different, right? So even the CPU is treated as a device. So the code which we are going to execute, right, our kernel, which I showed in the parallel for Lambda function, passed to a parallel for method, it can actually be executed even on CPU So CPU is also treated as a device, but it's not native execution on CPU. It's execution on CPU through some backend layer, and in DPC++ implementation, it goes through OpenCA layer. So it's not a native implementation on CPU. Again, it's a run through an OpenCA layer on CPU. It can be integrated graphics, it can be discrete graphic, right? It can be FPGA. So any device which is visible to the runtime, and this is important, that it is visible to runtime, which means you need to have a drivers installed, right? And you need to have a lower level API installed, backend available. So by default, the runtime getting a list of all devices, scoring these devices based on its own logic, and it is open source since the compiler sources are available, and itself SQL is a set of header files, right? This is the way how it's implemented. There is no need in the new compiler here. It's um, all implemented with a templated library. So you can take a look on that, and you will see that it's actually scoring like a CPU as it's a basic device. Then integrated graphics will have a higher rating. Then it will be discrete graphic card, which will be even higher rating. So that's the logic behind. But with a default selector, the quite nice feature is that at runtime, you can also control what kind of device you want to pick up. And it may be any device, right? So there is a spatial environment variable where you can actually control what number of a device. So you can get a list of devices with the numbers, what number of a device you want to use. And it's possible with a default selector. With our selector, it's still possible, but it will limit you to some domain, right? To some subset of the devices. For example, only to CPU selectors, to CPU devices, or to GPU devices, and so on. And the thing is that you even can create your custom selector and follow your own logic on how you want to pick up a specific device based on the naming of specific vendor or whatever. So it's very flexible, but in the simplest way, you can start with creating the default queue and controlling at runtime on which device you want to execute. So now the thing is that we do have a container, and we wrapped our data to this container, right? And this will help us to move data back and forth from a device and to a host. But the thing is that we also need to access this data somehow, right? The problem is not only in the copy back and forth, but in the way what we are doing inside the kernel with this data. And that's why SQL introducing the interesting concept of accessors. So actually, I would say the memory model, not just buffers, but buffers slash accessors, because if you use a buffer, then you need to use an accessor in your common group scope in order to allow you to access this data in the kernel finally. So you can see that what we are doing here is that we are using the get access method, which is a method available in the buffer class to get the accessors A, B, and C. And what we are doing here, we are explicitly specifying what we are going to do with this data inside the kernel. So with A, with a buffer A, right, an accessor A shows that we are doing read-only operations. And same with B, but with the C, we are doing write operation. And it means that under the hood, the runtime will care about the correct scheduling of a different kernel. So think about, in this case, we do submit one common group and so one kernel. By the way, this is the limitation by the standard, is that only one invocation of parallel 4 is allowed inside one common group submit operation. So you cannot write H parallel 4 here. So one parallel 4 for one submit stuff. Yeah, but there may be corner cases where you have some branching, like if else, but from execution point of view, it's only one parallel 4 which is allowed by standard. So think about multiple queue submit operations and multiple kernels, right? So in that case, the concept with buffer accessors allows us to build a graph of dependencies. So we may catch that, okay, for kernel 1, we are passing the buffers A, B, and C, right? And we are writing to the buffer C. So which means kernel 2, if it's getting C as an input, right? It cannot be executed in parallel with kernel 1. It will be executed after kernel 1 is finished. And this is all done automatically and so on. So I will have more slides later, but on the high level, these concepts allow us to schedule the execution of the kernels in the proper way, right? And then once we get our buffers, right? Once we created a queue to link with some device, we are submitting the common group to this queue, and we define the accessors to our data. Then we can actually perform a parallel for invocation and to execute some kernel, right? Some device code on the device. We actually need to set up 2 additional um, points here. Is the iteration space, right? So how many times we want to execute this code on how many execution units, right? And we need to index somehow the data, right? So we need to make sure that for each execution unit, for each work item, for each thread, we are executing this code on the different piece of the data. That's why we are creating this index, and we are accessing this index, accessing the data via this index inside the kernel code. Again, the concept is quite similar to the OpenCL or to CUDA or to any GPU programming. So this is quite common. Note that here I'm using a SQL 2020 syntax, which means it is quite simplified. So you don't need to specify templates. So this template deduction feature of C++17 is used. You can use auto type and not the explicit ID class and so on. But it's up to you to decide. Or even here, when we are setting the iteration space, it's actually templated range class, which is passed here. Note that, as you can see, the lambda functions are used quite extensively in the SQL. So it's an argument to submit method is a lambda function, and also an argument to parallel for is also a lambda function. But actually, you can pass any function object as a kernel to parallel for, right? So it shouldn't be lambda defined here. You can define the lambda function in your code itself, or you can even have a class and get a function object by overloading an operator and passing it here. So all this is possible. So we just need to pass some function object. I also wanted to highlight that in the past the syntax was a bit different. So there is no sense to follow the old syntax nowadays. But what I like in the exactly same code written in SQL older standard is that it's much more specific, right? So here you see that the buffer is templated, instantiated with float type. You can see that the ranges are more specific and all the classes are visible. But I wanted to highlight, so that's why I left this slide, is that you actually, for parallel for, you can also name the type of a lambda function. And this is maybe important when you're going to profile your code, because in the previous example, what's going to happen is the compiler will generate some random name for this lambda. since we are using unnamed lambda here, it will generate some name for this kernel. And if you will have many kernels in your code, it will be not so useful to get this automatic generated by the compiler names. While when you specify it explicitly, you will have more meaningful name in the profiling data. So that's the point I wanted to highlight. So it's not important to specify it, but sometimes I would recommend to follow this step. So now let's talk a bit more about ranges and the items and all that stuff. So again, range is a class which is used to describe the iteration space. It can be 1D, 2D, 3D, right? And there may be actually different classes used to specify the iteration space. So range is like a basic class which allow you to do the basic stuff. Then there is also a requirement to identify somehow the instance of element of the data inside the kernel code, right? And I showed earlier that you can do it with ID class, but it's only in case if you don't need any additional functions to query inside the code. For example, if you want to get the full whole range, right? Like here, you are not able to do it with ID class. So that's why, in principle, in SQL, there are three major classes how to identify your data inside the kernel. So ID is the simplest one with less functionality. Then it is an item class, and it has a wide range of additional features like get range, get ID, and so on. So you can get exactly the same here, right? The same IDX like here with a get ID function, but on top of that, you have many more stuff, including some, APIs which help you to calculate the index in linear mode, even if you have 2D ranges and so on. And the third stuff is ND item, and we will talk about it while talking about ND range, because in SQL, there are two principles in the way how you invocate your kernel. So it's basic parallel kernel when you are using the range and letting the compiler decide what will be the hierarchy of workgroups in your case, or you can control it yourself. But to go further, you need to understand the SQL thread hierarchy and mapping. So in the SQL, there are few basic concepts talking about instances of a kernels, instances of a device code. So the smallest, like the basic one instance, so just one instance of your kernel code is a work item. And then these work items may be grouped in the different ways. So if you're familiar with the CUDA, so work item is a thread in the CUDA. And any of these concepts like subgroup is a varp, workgroup is a block, and ND range is a grid, right? So any of this term can be mapped to something similar in CUDA or in any other concept of GPU programming. So this is the single instance. Then these instances can be grouped in the something larger called subgroups, which help you to map to CMD features of the underlying hardware, or can allow you to perform some operations on the subgroup, so a set of work items at once. And then these subgroups are organized in work groups. These work groups may have different dimensions, right? And this is done to more effectively map to underlying hardware, right? Because the underlying hardware doesn't have infinite capacity of execution units. So usually it is divided into some logical units, right? So it can be slices, sub-slices, whatever, but it has some specified amount of threads which can be executed on this of each sub-device or sub-slice. And that's why it is sometimes quite important to do this grouping of your work items of threads, and in order to map as precise as you can and perform the code as efficient as you can on the final target architecture. And then these work groups were forming the ND range. So the ND range consists of some amount of work groups. So you actually can control in the SQL the size of the work groups, right? You can control the size of the subgroups, size of the work groups, and finally, that's how you're specifying the ND range, right? You're specifying the overall iteration space and then the size of a work group. And this is why it is important. So as you can see here, it's like Gen 11 architecture, but more or less any architecture will be divided into some chunks, right? It will be some kind of slices or parts of your GPU, which has some dedicated cache, memory, right? And work groups are actually helping to map to this sub-slice, right, in a more efficient way, so that resources are properly used or efficiently used. Yeah, and the subgroup is pointing to one, let's say, CMD register in the execution unit. So you need also to keep in mind that the device memory hierarchy may be quite different from the host side. So what you need to do to know from the SQL is that each work item, right, in your kernel, it may have a private memory. So all the data which you declare inside the kernel, it usually goes to a private memory. It can access the local memory or so-called shared local memory, which is available for all work items in one work group, right? And there is a global memory. And it's obvious that the fastest is the private memory and the smallest, then the local memory, and then the global memory. So, and this kind of mechanism with work groups, it allows you also to care about these multiple levels of memory available on the devices and write your code more efficient. And that's why you can control it via the ND range. So in the beginning, we were introducing the range class. So ND range kernel is actually a different way of expressing parallelism, where you can control yourself what is the work group size you want to pick up. And this finally will allow you to fine tune a bit for performance. So I'm not saying so with the range, what's happening is that the compiler actually deciding what, or runtime deciding what kind of sizes to use, but it may be not always as efficient as you can fine tune it. So that's why we haven't done some kind of research in fine tuning and let's say additional compiler, maybe introducing quite soon some additional compiler options which will allow to based on profiling information to fine-tune these sizes of groups. So the syntax is relatively simple. So if in the past it was only a range class specifying the iteration space, right, the full iteration space. So now we're constructing the ND range class, and they're passing as a first argument to a constructor a full iteration space, and the second is a work group size, or sometimes it's called local size. So this is a global size, and this is a local size or work group size. So it's a number of work items in one work group. Yeah, and now you're using the ND item and not item class in order to identify the pieces of your data inside the kernel code. And there is also a rich set of additional APIs like getting the global ID, the local ID, and so on. And with ND range and ND item, you are getting additional functionality. For example, you can use the shared local memory. So it's not possible to use shared local memory, and it's done via the spatial accessor construction with a regular range class or item class. So it's only doable with a ND range and ND item. And the same with the barriers and other stuff. So it's more advanced stuff, and you're getting more advanced features with these classes, which you can use inside your device code. So now, quite interesting thing which was intentionally written in this code is this additional scope, right? You can see here that we are exiting out of this scope, which means we are destructing the buffers. So once we are destructing the buffer, the synchronization implicitly happens, right? So all the queues where these buffers are used will finish their execution. And here at this moment, we are safe to use our initial array or vector on the host side, because here we are guaranteed that the data is calculated on GPU and it's transferred back to a host memory. So that's why this additional scope is here. And that's why I want now to talk about synchronization in more details. So there are different ways of synchronization you may think about. So there is a synchronization within the kernel function, right? And there is a synchronization between host and device. So to control the synchronization between host and device, for example, you can use the destruction of the buffers, which I just showed you, right? Or you can call a wait member function on the queue, which will also block the execution and wait until all common groups submitted to the queue finish their execution. You can also rely on the DAG, right? A graph, which is done automatically and which enqueuing function objects in the correct order to a device queue. So this is about the synchronization between host and device. Within kernel, there are not so many options how to do it, and it's actually better to avoid it, but there is a barriers for synchronization work items, and there is no synchronization primitives across work groups. So you can synchronize within the work group, but not across the work groups. And there are different APIs, for example, the usage of subgroups, right? Which allow you to avoid the synchronization, explicit synchronization within a kernel function, because you can do some kind of a group operations, right? You can do some kind of a shifting or permutations of a work items if you need, with algorithms available in the subgroups. Host accessor is some kind of additional type of accessor. So we talked about the accessors which we define inside the common group scope, right, which help to access the data inside the kernel. But there is also a way to create an accessor in your host code. And this is a way how you can also synchronize the data to be copied back to the host if you construct this host accessor. So this is a simple example. So again, as usual, you will see that the queue is created to link to the device. We will have some kind of a data on the host, right? And we are putting this data to a buffer here. And we are submitting a common group as usual. And we can see a parallel for invocation, and this is a kernel. So what we are doing, we are subtracting 2 each time from each element of an array, initial array, right? So we are not adding an additional scope here, right? So that we are not actually destructing the buffer. We also don't use a queue wait here. We don't wait on the all common groups submitting to the queue. So there is no queue wait here. So we do the synchronization with the creation, the construction of a host accessor here, because once we construct it, we will wait until all the queues using this buffer finish their execution. And you need to be really careful to avoid the deadlocks with the host accessors in your code. So you need to understand this stuff. So that this kind of a constructor of a host accessor is a blocking call, and it will only return once all the queues operating with your buffer finished their execution. Yeah, but buffer destruction, it's what we already talked a bit, right? So it can be useful. You don't need always to create the scope in the way how I did earlier, right? If there is a function call like this, and we create a buffer sphere, so once we are exiting the scope, right, the data allocating on the stack is destroyed. Destructor is called, so that's why it is here quite safe to use the initial vector data, host data. So the data is copied back. There are actually many ways how you can control this copying. So in the buffer class, there are some additional options you can specify, like set finalized data. So you can specify to which initial array you want to actually perform the copy back, right? You can even disable the write back function. So if you don't want to write back to a buffer, for example, if you want to use the buffer in the device code, but you don't want to, you need it to calculations there, you don't need it to be copied back, right? Or you can transfer the data non-initialized to the kernel. So all these APIs, they are available in the SQL. And in the demo, we will cover a few of these additional options. So note that SQL itself is following asynchronous execution mode, which means, let's go back, which means that once we submit the queue, we keep executing the device, the host code. So if there is some code here, when we are going to proceed with this execution. So queue submit operation is not a blocking operation, which means we actually don't know at which moment exactly this kernel will be executed on the device, right? That's why there are two types of error handling in SQL. And since it's C++ based programming model, it's definitely following C++ rules, which are based on the exceptions. And this is so different from CUDA, which is error-based. And this may potentially create some difficulties in the migration of the code, but it's not, I wouldn't say it's difficulties, but more or less like additional manual work which you need to do. So this is a usual way how to catch the synchronous exceptions, which may happen immediately. For example, once you construct an object, for example, creating a buffer. So if something is wrong, you can get this synchronous exception. But you also can catch the asynchronous exception, which happens sometime later during the execution of your kernels, right? For example, when later the crash on execution of a kernel happens, but your host program keeps executing your code, right? You need to catch it somehow and provide an asynchronous exception handler in your code. So these are two basic concepts. So what I want to do now is let's go to the Jupyter Notebook Lab, which is available into DevCloud. I really encourage you so that after the training, you can do it yourself, you can pass it yourself. It's quite simple to get an access there to the dev cloud, and I think Klaus Dieter talked about it. And yeah, let me now go here. So I'm actually I logged in. So if you go to this link provided, you can find the different essentials modules to learn data parallel C++. So module 1, 2, 3, and so on, covering all the details as well as OpenAP offloading basics, which can be also useful. But today we are focusing with DPC++, and that's why I want to show you what is available there in these two first modules, and then later I will also show you what is available in module 3 and 4 and so on. So by just clicking it, you will open the Jupyter notebook on the dev cloud, and you can actually read. So all the basics we are discussing today, they will be they are quite well also described here in these paragraphs and this theory part. And then you can actually compile and play with some code even here. So what you can see that there are boxes here which you can execute one by one, right? If you click this button, then you can see that overwriting of this code is happening. So you can actually do whatever you want here, and you can see that in very basic, it's a very basic step. What we are doing here is we're defining a main function, creating the queue, and performing some very simple operation with a unified shared memory syntax. We have not covered this yet, but we will do it in a few minutes later. We will start to talk about unified shared memory. But this is just to show you the way how you can execute the code here. And then you go further, clicking the button, and you can see the progress. So note that on the dev cloud you have a different ways how to work, right? So you can use this PBS tool in order to submit your calculations on the nodes of a cluster, right? Or you can get a node in the interactive mode and do whatever you want on this specific node. So you even can do it in this way and directly go to some sources like here and compile the sources one by one. So for example, let me show you an alternative to using the Jupyter notebook is can we open the terminal, and you can see here that actually all the environment is already predefined, and you can get the latest of a compiler available, right? And you can compile any code you want here. So if we go to one API essentials, then to sources, then you can actually try to compile some simple code, right, and check what's happening and how it's running. So that note that here we are running actually on the login node, right? So if you want to go to some device, to some not device but computation node, then I just wanted to show you the command to do it. There is a way to. Something is wrong. There is a way to allocate the interactive node, right? And by doing this, you can actually get the not the login node, but the compute node where you can compute. So maybe later I will show you how to do it. And now I will more focused on the Jupyter notebook. So to submit some scripts or work to the compute nodes, there is also a special script available for you, which is called queue. And here you can see the way how the submission of a work is happening. So this queue sub commands to execute your code on some node with the GPU available is written here. So, and that's why you can see this nice output, like waiting, and once it's done, we are getting the the data back. What I wanted to show here is that, okay, we created the queue, right? And we use the default constructor for this queue. And you can see which kind of device was used. So it's actually integrated graphics available on this machine. You can see that we can get this data right in the code. So by doing get device, get info, we can actually display the name of the device, right? So each queue actually constructed with the usage of our subclasses like context and device. And for each device, you can query for the additional information like the sizes of workgroups and so on. So there is plenty of information which you can get. Yeah, going further, there is also this simple vector addition example explained here. You can see there are even some steps which you need to follow in order to compile the code. So it's up to you to do this. My intention was to show you that there are some exercises that you can follow yourself. There is nothing very special here. As you can see, we can go briefly through the code so that you understand. Again, there is always host data, right? There is always construction of buffers in these examples. Yeah, you need to uncomment the construction of a buffer for a second vector, for example, here. And then the queue is always created. So in this case, it is actually passed as an argument to this work function. But in the main code, you will see that the queue is constructed. And it's up to you to play with it. So to control the device selection yourself. So what you can do is you actually can modify the code here and pick up whatever you want, like any different selector, and you can pass it as an argument to the queue, and then the code will be executed not on the CPU but on the GPU, or not on the GPU but on the CPU, right? This is also was possible to do with this initial code, right? So if we want to avoid the usage of an integrated graphic but run this kernel on CPU, is we need to rewrite and we need to rerun this code. And once it's done, we will get our device printed here. I will go back to it. So in here again, we do the queue submit operation and we're creating the accessors, right? And then via these accessors, you can see that in this specific case, we are specifying explicitly the class which we want to name this unnamed lambda with this name, actually. And the way how the synchronization happens here is a queue wait operation, because as I told earlier, there may be some host code here. So there may be some calculations done on your host code. The execution will keep happening on the host side after the queue submit. And only this is a point where we are waiting until all the kernels from this queue are finished, right? And note that there are actually there is also a host accessor here, right, which is maybe too much. So that's the idea of this exercise, to play and understand what's happening. And if you're going back, you can see that I've changed the device selector, right, in this code to be a CPU selector. And what's happened is that the device which was picked up by runtime is Intel Xeon now. So it's now running on CPU, but it's running through the OpenCL layer. So when we execute this command, right, CLLS, we can get the information about which device are available on your system. And This is quite useful to do on any node you are getting. So let me go back to my slides. Okay. I just cannot switch to my presentation anymore. So any questions from your side at this moment while I'm trying to restore my presentation? Any questions on? Yeah.
There's a question in the chat.
Yeah.
It says, at which point are data transferred between host and device? Is system implementation dependent? And can I influence that?
Yeah, so you can influence that, but with a buffer accessor memory model, it's not so explicit. So if you want to control it yourself, then there is an alternative memory model which is called unified shared memory, and in this mode you have a way to explicitly control the moment when the memory data transfer is happening. With a buffer approach, you don't have this explicit control. So I just wanted to show you that on this terminal, you can actually allocate some compute node on the dev cloud. So instead of going through Jupyter Notebook, we are allocating the node in the interactive mode, and this is the node which I got. And here, actually, you can query for all available devices, and you can see that there is a level 0 runtime installed here, and OpenCL runtime installed for GPU, drivers installed for GPU. There is an OpenCL for CPU, and also FPGA emulation platform, actually through OpenCL as well. And there is a SQL host platform, so it's a way to a fallback mechanism which allow you to execute on your host natively, even if our APIs are not available on your machine. So now let's go back to the slides, and I want to talk a bit more about the way how the compilation happening and what's happening under the hood. So now you have an understanding how a basic SQL code looks like, right? It's simpler when it looks like, because in reality you may have a large code, right? But usually there are not so many places in your code which you need to offload to GPU, right? You need to know your hotspots, and you need to try to accelerate these hotspots in order to speed up overall application performance. So when you need to transform these hotspots to a SQL code with an invocation of a kernel, right? Once you did it, then you need to compile this source code with a DPC++ compiler, for example. And this is what's happening under the hood. So the compiler is able to understand that your code consists of two parts, the host code and the device code, right? And for the device code, so for host code, the compilation goes in the usual way. It's just the integration header is generated for the device code. So it's just an include header file which will be used to compile the rest of your host code. And that's how the host object file is generated. But the other path in this case is how to compile your SQL device code, right? So, and here a SQL device front-end compiler is used. It generates an LLVM IR, right? And then there are many phases like LLVM link, and we translate this LLVM IR to this PRV binary format here. So, and this is a core format which is used in our implementation. So we have two choices with this binary SPIR-V device code. We can just wrap it forward to the object file and pass to the linker here. And in that case, we will need to invoke a just-in-time compiler at runtime, because SPIR-V is some kind of a representation which is not a target instruction set, right? So at runtime, running on some device, on some system with, let's say, discrete graphic, runtime can detect what is the architecture and then translate this SPIR-V to a target binary. But you have also a way to control it yourself by specifying additional options to the compiler. So if you do like this, then you are forcing the compiler to avoid this default just-in-time compilation model, and at compile time to go through this path. So to migrate or to translate SPIR-V to target binary and to inline this target binary to a final fed binary file together with a host object. So the advantages and disadvantages are quite obvious. If you want to leave a SPIR-V in the binary and use the just-in-time compilation, then at runtime the compilation of the kernels will be happening at runtime, and it will cost additional overhead. But it gives you more flexibility, right? Because in that case, you can run on any device. While if you're using ahead of time compilation, you are specifying the target device at compile time, which means if you will bring this binary then on the other device with a different architecture, you will be not able to run it there. But there is a possibility to mix both concepts, so you can actually guide the compiler, okay, leave a SPIR-V format, but also generate the target binary for the specific device. So it will increase the size of a fed binary, but give best portability, for example. Yeah, so you can gather more detailed description of this process by following these links, and also this documentation is quite important. So it's explaining this offload ahead of this kind of compilation is quite often called ahead of time compilation. And note that actually, so I started my presentation talking about compiler drivers, right? So when you type dpcpp and then the name of your source file written in SQL, right? What's happening is under the hood is at least two different compilers are involved, right? One is for the host code and the other for device code. And by specifying this option, you are actually, especially this option, you are actually passing further the compiler options, not to the host code, but for the device compiler. So this is finally in our implementation a way how to pass this option to Intel graphics compiler if they are compiling for GPU, for Intel GPU. So under the hood, it's a host compiler and it's IGC, Intel graphics compiler, which is invoked for Intel GPUs. Again, if you follow just in time, if you follow ahead of time compilation. Note that this abstraction model which SQL introduced for us, it's really great. It's hiding a lot of details, right? And it allows us to be agnostic to the vendor implementation under the hood. But there is always a payment for it and the cost. And the cost is that we have this kind of multi-layered pie under the hood, right? Because we need to have a SQL runtime. So I talked that runtime, a SQL runtime, for example, builds a graph of dependencies, right? So it's doing the scheduling, it's doing the memory management and device management. So all this happening on this runtime, DPC++ or SQL runtime layer. But under the hood, there are other layers because to allow you to use different implementations under the hood, like level 0, OpenCL, CUDA, whatever you want, we also introduced the additional plugin interface layer, right? And then it allows you to finally at runtime control with which lower level API you want to execute your code. So it may be quite different. It may be level 0, it can be OpenCL, and it finally means that any abstract high-level code written in SQL is at some moment is mapped to the OpenCL APIs or level 0 APIs, or if you so this picture is for Intel architecture only, but if you target other vendors, it can actually finally go to the level of CUDA runtime and use the CUDA under the hood to target NVIDIA devices. You have a way how to control it. So you have two options. So there is a environment variable called SQL BE, which you can set to different values and switch between different plugin interfaces. Or you can use, which is a bit outdated and deprecated, but still quite useful in my understanding. That's why it's not removed completely. But we have much more powerful environment variable to control more than only plugin interfaces, and which is called SQL device filter. So, and here I can show you a few use cases. So the syntax is as follows. You specify the backend, then semicolon device type, semicolon device number, and you can shorten it whatever you want. So I showed you quite useful command to get the list of all available devices in your machine, right? It is called SQLLS. So it's available once you installed one API in our binary folder. This tool is installed and available. It helps you to list all the devices, and the devices listed here means that you have a driver installed, right? A hardware driver for this device, and you also have a runtime, so that this runtime is visible to the SQL runtime. So if you have follow to all the instructions correctly, then you will get these devices listed. And what you can do is you can, for example, set to use this specific device by just setting SQL device filter to 1, right, or to 3, whatever you want. Or you can filter it to a subset of devices. For example, you want to use all OpenCL devices, and then you can set SQL device filter equal OpenCL, and so on. Or you can control and specify OpenCL and then specify CPUs only, right? So it's very flexible. You can specify any GPUs. You can avoid asterisks if you want. And it's following two purposes. So you want to specify the device which you want to use. And the other one is you can avoid the loading of plugin runtimes, only relevant plugins into your runtime. Because what's happening by default is that all plugins are loaded by default. So let me actually show you how it looks like. So now we are on machine. There are these devices available, right? And the thing is, we compiled this code earlier, right? And it's running on GPU. So what you can do is you actually can control the backend via this environment variable I showed earlier. So you can specify a backend and run. And from where, so you're by way getting the message that deprecated and it's better to use SQL device filter, but you can still use it. But you can see that it's still Intel UHD graphics device use. So that's quite interesting. So what I want to show you is that we actually also have an additional environment variable, which is called SQL PI trace, which help you to get some additional data from a runtime on what kind of plugins were used and so on. So, and you can see here that so this is the data which we are printing from our code itself, but this is the output we are getting additionally, like some kind of debug traces we are getting from the SQL runtime. And you can see here that actually 2 plugins were founded and loaded. So it was OpenCL plugin and it was level 0 plugin, and both were loaded, right? And since we specified SQL backend to be OpenCL, we pick up the Intel OpenCL backend. So it's not level 0. Now let's check what's happening if we don't specify SQL backend. What is the default backend used? And you can see that the default backend which Intel DPC++ implementation using is level 0. So which means it's a different set of APIs which is finally used for your SQL code on the lower level. And with the SQL device filter, right, you have more control because you can specify OpenCL only, for example, right? And in that case, you can see that only this plugin was loaded. So this is the difference of SQL device filter versus SQL BE environment variable, because here we were actually loading both plugins, right? Even we were using only OpenCL, but both plugins were loaded. Here we're loading only what we really need. So I showed you some quite important environment variables by doing this demo. So number 1 is how to control at runtime the available devices in your machine visible to your runtime, right? How to control backends with SQL BE option, and actually how to enable debug logs. So this is quite useful for you to understand what's happening under the hood. There are different levels of this logging. So I just use the initial one where we only print the information while device is loaded, but you can extend it and get more information on what kind of functions are called under the hood, and you can see some kind of lower level detail. So once you will go and deeper debug your applications, you will definitely appreciate the availability of this kind of stuff. And the maximum level is -1 when you're getting even more stuff. And you can see, by the way, here that there were some events happening, right? Some implicit synchronization, enqueuing of the kernels, and other stuff. So this is how you can understand at which moment, for example, the memory was deallocated. But as I said earlier, this is a bit tricky to understand the moment when the memory copy itself is happening with this implicit memory model mode. So now we are going back to the slides, and we will talk about this in more details. So in the slides, you can find that I provided this data on the SQLLS, and also I'm pointing you to some very useful tools which you can use. For example, in the open source project, we have some code written on, I think, level 0 or even SQL. I'm not pretty sure. I think it's written on level 0 directly. So that there you can get a lot of information about your device itself, which is hard to get in any other way. So that you can get the physical number of execution cores, a number of slices, and all that stuff. So bookmark this link. This is quite important set of different tools which may help you significantly in the debugging and troubleshooting. Yeah, and now let's talk about the different concept of managing your memory, and it's called USM. So definitely buffer memory abstraction is very elegant way of expressing data dependencies. Nothing is required from your side, but there are some issues with this concept, right? And one is quite often we want to control this memory management ourselves, the moment precisely where the data transfer happens. And it also quite nice way on how to move from the alternative pointer-based programming models like CUDA, for example, where the pointer-based model is used, right? So mapping this to buffer concept may be a bit tricky. So that's why this USM is a complementary to buffers. There are pros and cons to use both technologies. Let's now talk about unified shared memory concept. So it's coming from the fact that we on the hardware level and on the software level should guarantee that the same pointer can be referenced from the host side and device side. And this is quite important in the unified shared memory concept. So we have a look on our memory like on the continuous piece of memory where we can get a pointer which is valid and can be used from both host and device side. And in SQL, there are actually three different allocation types you can use. So it's malloc device, malloc host, and malloc shared. And depending on what you want to achieve, you may use any of these memory allocations. So we will talk about it. So let's start with the explicit data movement and the usage of malloc device allocation. So from the structure of the code, nothing really changed for you, right? Except the fact that now we don't have buffers and accessors anymore. So what's happening now is we still have a queue, we still have a host data, right? But what we are doing except wrapping this data to some to some buffer is that we allocating the memory on the device from the host side via the malloc device call. Note that in contrast with almost all our APIs, this call is blocking. So it means that once we are going to the next statement here, the memory is allocated on the device. And keep in mind that for memory allocation, you need to pass the queue here. So there is an alternative to pass the context and device, but you are allocating the memory for the specific queue, right? Because the queue is finally linked to the specific device. Okay, then we are doing some initialization of our host data, and what we are doing further is we are doing an explicit memory copy to this location on the device, right? And we are copying the data from our host array to this device array. So back to the question about the explicit controlling of memory transfers. So in this memory model, we are explicitly specifying it, and that's why it's happening right now. Note that this call to memcopy is actually non-blocking. So again, the only blocking call here is malloc device. A submit is non-blocking, memcopy is non-blocking. That's why we need to care about correctness of this code, and we can invoke a queue-wait here, or we can invoke a wait actually here, which is even better. Why it is better? So there is actually a difference between this this statement and this statement. So, and the difference is usually in SQL, since it's event-based mechanism, each time we perform this operation, qsubmit or qmemcopy, we are getting an event return by this API, which means that here we're returning some event, and we can actually wait on this event and not on the full queue. So queue-wait is blocking operation, means we are waiting until all the common groups submitting to a queue are finished. when we wait on some event, we're only waiting until this specific event is happened and not other events which may be happening for the queue. So this is an important difference between specifying wait here, because in that case, we are invoking wait on the object of the event class returned from memcopy. And this is we are calling a wait on the queue. But in this simple code, it doesn't matter, right? Because there are no other events or common groups submitted to the queue. But in more complicated scenarios, you will see the difference. So we're doing the wait to double check that the memory is really copied, so that on the device we have this data. And then we are performing again the same stuff. We are doing queue submit, we are performing parallel for, and we are passing the lambda to parallel for, and this is a device code which will be executing. Then we need to double check that, okay, this kernel finished the execution. We are copying the memory back from the device to the host, again waiting, and that's it. Actually, when we're deallocating the memory and so on. So this is an explicit data movement mode with USM. There is also an implicit data movement way of doing, and in that case, you will use the host and shared allocations. And the idea of implicit data movement is you also allocating the data, right? You're using the malloc shared API. But the thing is, you don't need to control memcopy operation. So it's something in between buffers and explicit data movement, because here you're controlling the moment where you want to allocate the data, right? But you don't control the moment where the memory is actually copied back and forth from the device. So it is covered by the runtime. And that's why we just allocate the host array, because we allocated it with malloc host. We now can easily use it in the device code. And with malloc shared, it means that this shared memory is migratable from device code to the host code. So it's some kind of shared array which you can now use in the both sides. You can write to this array in the device code, right? And you can use this shared array on the host side as well. So there is a basic recommendation is maybe to start with implicit data movement in your case, and for the part of your code where you want to fine-tune the moments where you copy the memory, because it's known to be a bottleneck, right? The moment when the memory is copied. So sometimes you need to keep the memory longer on the device and not copy it yet, and that's why you will probably need to fine-tune the moments of memcopy operations. But this can be a good starting point to start with implicit data movement, and then for the hotspots, for the important parts of your application, to fine-tune it for a very explicit data movement concept. Interesting that in this case, no accessors required, right? Because we're explicitly doing memory management. That's why dependencies must be controlled yourself via the events. So you can wait on event, as I explained earlier. You can wait on the queue, or you can use a special depends on method inside a common group. So now we will talk about it. So imagine you have multiple submit operations and multiple kernels, A, B, and C, right? And you're writing to the same data. So we're allocating the data via malloc shared, and we're not controlling via memcopy explicitly the moment when the data is copied. But we see here that we actually need to execute these tasks one by one, because otherwise there may be a data race happening, right? We will be writing to the same shared data object. So that's why we are specifying wait here, and this is a wait on the event returned by the queue submit. So there is an alternative way how to do this, and the alternative way is to track these dependencies via events. So as I said, many of the SQL APIs returning an event, and the submit operation is one of these APIs, so that we can track the event 1 here, the event 2 here by submitting the different task, right? And then we can specify the method of the handler class, which is called depends on. We can specify that this queue actually dependent on event 2. Or there is other option. What you can do is you can specify to a runtime is, okay, the queue should be constructed as an in order queue. And it means that by default, so it doesn't mean that we will block after each of the submit operations. So it's still non-blocking. An execution of a host code is still possible. But the thing is that the graph of dependencies will be constructed in a way that each next kernel will be always executed in a row one by one. So it affects the way how a dependency graph is constructed under the hood. So note that actually you have an option even to print this execution graph. So there is an option, debug option, to print this data if you wish, but I rarely seen the problems with that. And it's quite important to understand this kind of synchronizations, implicit and explicit, because finally, when doing profiling of your code, you may see on vTune that some kernels were not executed in parallel on different tiles or parts of your GPU, right? And you may be getting some, you may be puzzled by why it is happening. So it's quite often may happen because of this implicit scheduling with the usage of graphs. And note that again, with the USM, the graphs is not built automatically. So you are doing it yourself by specifying depends on. There is actually the different syntax, and I think it should be shown here. So instead of writing depends on, there is a simplified way of specifying dependencies, and there is actually a simplified way of invoking the parallel for. So we haven't seen this before, and I want to highlight here that in SQL 2020 there is a feature called shortcut queue, which allow you to avoid explicitly to write queue submit and then parallel for, because for the use case with the USM, it's not mandatory, right? You don't need common group scope in case of USM because you don't need to create accessors there. And that's why it is simplified, and now you can invoke a parallel for directly from the queue. And it avoids like additional lines of code for you, right? And moreover, it's one simplification. The other simplification is, in that case, you don't need to write depends on, and you can pass these dependencies as a second argument to the parallel for invocation. And it will have exactly the same effect like writing like this. So you can see how more dense code is. So you're saving a lot of lines of code by doing it. And this is quite nice. So I would say that nowadays I can see this kind of programming with SQL 2020 much more common. So what is important with buffer accessors, you are getting a powerful abstracted model where runtime cares for you about the memory copy operations, right? And building the dependency graph automatically, controlling the scheduling the execution of the kernels. While with unified shared memory, you may control the moment where you allocate the memory, where you actually copy the memory with the explicit USM. In this case, it's your responsibility to care about correctness of kernel scheduling. So you need to specify or help to build the graph of dependencies by passing these events to the runtime. So I think that's it. I don't want to go deep dive in the subgroups. I would consider a bit more advanced stuff. So I want to highlight that I collected for you a set of useful links here, and you can see that all runtimes and all compilers are actually open source. So you can see that the DPC++ compiler is open source, and you can find the sources here. The compute runtime, which means level 0 and OpenCL runtimes, are also open source, and the graphics compiler for Intel devices is also open source. And I would really recommend you to start the learning, so you now have a good introductory level, right? So you can go a bit deeper by doing the different modules on the dev cloud. And I have 5 more minutes, so I want to leave it for question and answers, or to show you a bit on the dev cloud, a bit more modules which you can pass. But I would also recommend to start with this DPC++ book written by our senior architects, which covering all the topics in so many details with a clear explanation why you need to do this and so on. So it may answer many questions for you. Yeah, so it's time to ask your questions. So feel free to ask your questions right now.